Welcome to Unit 5. Make sure that you've got your slides open for acid-base foundations. So what's nice about the majority of this lecture is it's a revisit lecture. About 80% of it is. There are some new things. But this is one of those lectures that could have easily been in Unit 1, but I didn't put it there because it fits really well right here before we start harder stuff tomorrow. So my hope is that you recognize a bunch of this from honors. It's also the reason that I'll be going slightly fast through things like Bronsted Lowry, which can be challenging sometimes. So I hope that you'll go and find the honors videos over these topics if you feel like I do this too quickly. And of course, reach out to me for questions. Y'all ready? New unit? Feeling good? Let's do well. Acids and bases are a certain type of substance that have very predictable behaviors. You most associate the identification of them as by thinking that acids start with H and bases end with OH, which is fine, but that's if they're Arrhenius. All right? The word Arrhenius means exactly that idea, that acids start with H, and if you put them in water, they make H float around. But hey, not just H float around. Do y'all remember this substance here? Hydronium from last year? Add that to your notes. Hydronium, the H3O plus, it might be elsewhere in the slides. I'm not 100% sure, and I meant to check before this period started. But hydronium, the H3O plus, and hydrogen ion, H plus, are synonymous for all our purposes in here. I mean, they're technically different from each other. But for the way that we analyze acids, H plus and H3O plus are going to be the same thing. So anyway, if you drop an Arrhenius acid in water, it produces H plus or H3O plus. And if you drop an Arrhenius base in water, it produces OH minus. So those definitions are fine, and they really do serve your purpose most of the time in here. But that's not the only acids and bases. I introduced a weak base to you called ammonia in Unit 2. Who can remember what the formula for ammonia is? NH3. Doesn't have OH in it, doesn't even have O in it, but it's a base. It's a weak base, but it's a base. What am I breathing out right now? Carbon dioxide. Very good, because 2 people last period said oxygen, and I just kicked them right out of the room. There actually is your lungs don't convert all of it, so they weren't really wrong, I guess. But it's CO2. You know what's interesting about CO2? It's acidic. Doesn't start with H, but carbon dioxide it has acidic qualities. It's just not Arrhenius. Arrhenius acids start with H, and we're obsessed with that idea, which is a good teaching tool. But not all acids start with H. Not all bases end in OH. That is an Arrhenius definition. I need you to know that. But when they're dumped in water, Arrhenius samples do produce those predictable items. Now, here's something that is a little different from last year. And it's really the basis for the pH scale. Like, I'm about to go over this number down here, but see that number 14? That should really make you think about acids and bases, right? Because we know that pH scale that we studied last year is 0 to 14. And what I'm about to go through is why those were the numbers chosen for that scale. Let's draw a picture together. Let's say that I had a beaker that was full of liquid water. That's a cursive L, a cursive lowercase l. All right. So it's this. All right. Let's see if it's water. Just kidding. I stole it from a student. So it's full of water. Now, it's full of liquid. Is it water? Is it water? It's water. It's water. So it's full of liquid water. Now, here is the potential of this sample right here. It can be at equilibrium with H plus ions and OH minus ions. It can naturally, while it's just chilling in here, dissociate into those ions. But listen, y'all hear it? Listen. Do you think right now that it is mostly liquid or mostly random ions? What's it sound like to you? Liquid. It's all liquid. This thing is almost 100%. Yeah. Is almost 100% liquid. So I've got this dissociation idea, this equation, with the reactants over here and the products over there, but we just agreed that in the case of water, it's almost all liquid all the time. If that's true, what is true about its K value? Big or small? Small. And the blankness in the room is the reason a lot of y'all didn't like your test scores last week. Because this was foundation for equilibrium. If K is a small number, less than 1, then the reactants are favored. So the K for water has to be a small number. Because in any scenario where water is just chilling, even though it's got the potential to do this, it's doing this. The reactants are favored. So K is small. There's the K value for water at the very bottom of the screen. By the way, everything in blue on that screen is on your formula chart, so that's good news for you. But the fact that the established K value for water that's just being water has that 14, it's really a little number, right? E to the negative 14. That's where the pH scale was born from. But anyhow, this is a really important idea because mathematically, the way that this talks to each other, it's also what's written on your screen. But a real important thing that you're going to be able to do is if you have the concentration of hydronium or H plus, because they're the same, or the concentration of hydroxide in a solution, you can always find the other one. The reason you can always find the other one is because you always know Kw. It's a constant value, 1e negative 14. So since you always have that number, if you have at least, if you have one of those, you mathematically have the other. And you'll see today and tomorrow and Thursday that that's a really important idea that you'll be using a lot. But it's born out of this idea. Okay, let's go more classical. This was half of your acid base unit last year, was the information on this screen. So let's remember a few super foundational things about studying acids and bases. First off, we want to remember that there are two scales that are operating at the exact same time. All right? We've got a pH scale that runs from 0 to 14. And at the exact same time, we have a pOH scale that runs the same direction. But I'm going to draw this one backwards. And for those of y'all that remember the class from last year, you know why I'm drawing it backwards. But hey, you can relearn it right now if you want to. In the middle, of course, is 7. No matter which scale you're looking at, a pH of 7 and a pOH of 7 are both neutral. All right? So both of those samples are neither acidic or basic. On the pH scale, if you go this direction, that is where the bases live. And if you go this direction, that is where the acids live. In regard into drawing conclusions about your substances. All right, so a pH of 8 is a base. That's what you want to be able to say. The pOH scale exists at the exact same time as the pH scale in a substance. All right, except the numbers work the opposite direction. So between 0 and 7, it's a base. And between 7 and 14, it's an acid. And you can get tricked on my questions pretty easily if you don't take the time to figure this out. That they are mirrors, which makes them reversed. So what we tend to do is deal with solutions where we're like, okay, well, we have a pH of, let's say, 10 in that solution. A pH of 10. Is that solution acidic or basic? It's basic because if you're on the pH scale and you are between 7 and 14, like 10 is, then it is basic. The mathematical connection here is the idea that pH plus pOH equals 14, which is written on your screen, but that is always true. pH plus pOH is equal to 14. So what must the pOH be here? 4, because 10 plus 4 is 14. And on the scales, if you have a pOH of 4, which would be like right around this area, is it acidic or basic? It's basic. The idea is even though the numbers are dramatically different, the conclusions you draw are the same because they're describing the same substance, right? This has to be either basic or acidic. So it's basic because the pH is above 7, the pOH is below 7, both of which make it a base. You were led to believe last year that you cannot break the pH scale, and you can. All right. As the screen says, you can have a pH below 0. You can have a pH above 14. Same with pOHs. It's just those are super highly concentrated, and you will see that scale break. You will not have to justify why it breaks or what that means outside of the scale. You'll just need to know that those two numbers together have to always equal 14 no matter what. And you'll see what I'm talking about here in a few examples. So, with that said, let's start our first set of calculations. If you don't have a calculator, grab one. There's some scattered. Now, sadly, the first thing that I have to do is go over a significant figure thing. A real bummer about pH that we don't cover in honors is that it's got weird sig fig rules. Let me show you what I mean. If I had a pH of 8.56, is that acidic or basic? Basic, right? Because it's above 7. All right. However, in terms of sig figs, this is based off logarithmic ladders, which again, you're not going to have to justify logarithms in here. But because of that, the number to the left of the decimal tells you where on that times 10 you live, and the numbers to the right of the decimal are the actual quantity. Again, you're not going to have to explain that back to me. I need you to know that when you're looking at pHs and pOHs, that all the significant figures lie to the right of the decimal only. This figure only has 2 sig. Because again, the digit to the left isn't a measurement, it's a magnitude of logarithms. Yes.
Does that mean that like all the digits to the right of the decimal?
All of them, no matter what. Because even if there's zeros, there will be a decimal present, which would follow the normal rules. So if that's true, and let's say that, new example, let's say that we had a pOH of 9, and it was written like that. First off, in this new sample, what's the pH? 5, because pH plus pOH is 14. That was an easy question. 5. But how many sig figs do you see? 3. There's just 3. There they are. Y'all, this is going to mess with you more than you think it is. I know it sounds really easy, but you're going to have problems that have molarities talking to pHs, which means both sig fig rules are going to be interacting with each other, and y'all mess it up all the time. So you need to be very aware of your sig figs so you don't lose that FRQ point. Let me show you what I mean. All right, check out that top example. All right, it says that the H plus concentration is 1.4 E negative 3. All right. I have a formula that says that if you know the H plus or the hydronium concentration, you can just plug in to this to find pH. The pH is the negative log of the H plus concentration. So let's plug that in. In order to find the pH, it'll be negative log, which are just buttons on your calculator, of the H plus concentration. Get to an answer, but have the correct sig figs. Anybody brave want to yell it out? It's not it. 2.85. 2.85 is the pH. Because this molarity has two sig figs, because it follows normal rules. The pH has two sig figs following pH rules. Careful. And then you could automatically find the POH, right? Because we know that if you add these numbers up, they equal 14. So without even thinking, I can figure out that the POH in this case is 11.15. We all right? Let's do another one. In the next one, it again gives an H plus concentration of 7.11 E negative 11. All right. But I know that if I have an H plus or a hydronium concentration, that all I have to do is go negative log of that number. It will give us pH. Let's draw a card for this one. Get the correct sig figs. Right? Let's go over to cluster number 2. It's a full cluster. Yay. Cluster 2, seat 6. What'd you get, 2-6? Perfect. That is the only correct answer is 10.148 because both expressions have 3 sig figs.
I thought the big things were.
For the pH it is. This is a molarity. Molarities follow normal rules. pHs follow pH rules. It's inherently confusing, but it's our job to keep it separate. Hey, what's the the POH here? Yeah, 3.852. Those two numbers always equal to 14. That should be the easiest part of this, but it's going to be a big. We're going to be doing it a lot. So, what? I heard he's teaching it. Felt like you were talking about me.
Of course.
Hey, hey, the last one's kind of has a little twist on it. Let's look at what that last one is. The last problem doesn't give us an H plus, it gives us hydroxide. It says that the hydroxide concentration is 10.1 molar. Your notes tell you that if you have a hydroxide concentration, you can still go negative log, but it won't spit out pH. It'll spit out POH. All right, so you've got to have that separation. H plus and H3O plus always talk to pH because those are hydrogen, those are acid compounds. Hydroxide talks to POH. All right, there are two separate worlds that are just living near one another. So we can say negative log of this strong sample, but realize that it's going to spit out a POH because it's OH instead of H plus. Here's where you get your fun, your most exciting moment of the day is the answer to that. Without telling me the answer, why do I think it's so exciting? Because it's negative. The only correct answer is negative 1.004. I hope you're not still messing up sig figs. There's 3 sig figs under my hand right now. 3. And now there are 3 over there because we have 2 different sets of rules interacting. All right? Hey, if the POH is negative 1, is it acidic or basic? Super basic. All right? Just look back at our previous thing. If you have a POH below 7, it's basic. Look, this is way below 7. So far below 7. Like, this is dangerously basic. Here's a fun question. What's the pH?
15.
Exactly right. 15.004. Because no matter what, the sum of those two numbers must be 14. So it's super basic still, right? The numbers agree with each other. Both of those values say it's highly basic. Practice coming on Canvas. Any questions right now? All right, let's keep rocking and rolling. Now, last year you were asked to go the other direction, which is this formula here. But I want to show you that while the formula is easy to use, right, and that's if you're given a pH, can you go to the concentration? I want to show you the weapon, that really the best way that I hope that you think about these foundational calculations. Make this list with me. We want a pH, which talks directly to H plus, and then we've got POH, which talks directly to OH minus. So again, these two dudes are connected, while these two dudes are connected. But most importantly, if you have one of the 4 numbers, then you have the other 3. And that's an important weapon for you to understand you have in your arsenal as things get more challenging tomorrow. If you know one of those, you have the other 3. Look at the first example here, 7.41. It gives a pH of 7.41. Now, you can start going to any of them from that number, but let's go to his friend first because that's what this slide is actually pushing. If you're given a pH but you need the molarity, the equation is 10, always the number 10, to the negative pH. So what I'm going to do then is I'll go 10 to the negative 7.41 will give me the concentration connected there. But watch your sig figs. Again, there's the miscommunication there can mess you up. I get an H plus of 3.9 E negative 8. Both of these values have 2 sig figs. It's your job to speak up if you don't see it. Some of y'all's looks on y'all's faces like freak me out. I have nightmares about y'all's faces. All right. Now, we can continue going however we want to go about this. Like, what do you think the easiest way to get POH is right now? Yeah, we know that those two numbers equal 14. So the POH, I can tell right away, is going to be 6.59. But stop writing for a second. Look here. I need you to really hear what I'm about to say. The way that you get to that last number, there's two primary ways. There's an easier way and a more annoying way. The easier way would be to go 10 to the negative that. All right? Because it works the same way. If you go 10 to the negative pH, it gives you that. If you go 10 to the negative POH, it gives you that. And that's fine. You're welcome to do it. However, on last year's FRQ, there was this type of question. It was wordier, but it was basically having the student do this. And when it got to that last one, that last lettered part of the FRQ, it said find hydroxide. I can't speak. Find hydroxide concentration. Use KW in your calculation. Use KW in your calculation. That was mean because instead of just going 10 to the negative that, which would give you the same answer, you had to show that you know how KW talks to it. So I need you to know how KW talks to it. We know that this is true from a few slides ago. We also know that KW is 1e negative 14. That's given to you. It's a constant. And look what I already have. So if you put in 1e14 and for H plus into H3O plus, because they are synonyms, you put in the 3.9e negative 8, you can find OH minus using KW. So it's not a lot harder, but it's a different route to the same number. So I do need you to realize, though, this down here. Algebraically, I mean, I believe you can do it without me saying this, but do realize, look here, that KW divided by one of those values gives you the other value. Listen to me say that again. KW divided by that gives you that. Or KW divided by that gives you that, which you could prove by manipulating anyway. But sometimes you like hearing it. So in other words, what I could do is I could say KW, which is 1e negative 14, divided by H plus 3.9 e negative 8 will give me OH minus. And in this case, I get an answer of 2.6 e negative 7. So this method and this method get you to the same answer, but it's good to have them both in your bag of tricks in case College Board gets creative on you. I want you to find all four numbers for the other example. There's another example over there. Find all four numbers from the 0.23. I'm giving y'all automatic notes credit for today, since we didn't have that much in a weird spot. But I'm gonna check your notes tomorrow. If I call on you, you can give me any one of the numbers. All right. So focus on your favorite. Let's go over to cluster 2. Yay, we're back. C3. Hey, 2, 3. Which one do you want to give me? I knew it.
13.77.
Y'all like that number? All right, because we know that pH and pOH equal 14. All right. Somebody yell out the H plus number. Anybody clearly? That's not what I got. That is what I got. Yeah, 1.70 E negative 14 molar. Of course, to get that, the easiest thing to do would be 10 to the negative that number. Gives you that. All right. Now, to get here, unless I'm told to do something different, I'm going 10 to the negative that, because 10 to the negative POH gives me that. Or we could go all KW and be fun and tricky, which would be KW divided by H plus is OH minus, and it'll give you plus or minus 1,000th of the same number, which is fine. But for the hydroxide value, I get 0.589. All of them have 3 sig figs. Who's got questions? All right. Yeah, want to keep going? I still got 15 minutes of fun for you. Sorry. Maybe it'll go faster. Bronsted Lowry, yeah? Anybody have flashbacks of that? What's funny about Bronsted Lowry is it takes 2 lectures in honors to teach Bronsted Lowry, and they get 2 slides in here. It's because y'all are so smart, though. There is no reason for Bronsted Lowry to scare us. Look here. You move a proton. That's all you do. You have a reaction or a substance, and you either give it a proton or you remove a proton. For us, though, a proton is going to be a hydrogen ion. If you think about what a proton is, it's an H and a plus 1. I'm sorry. It's a proton is going to be a plus 1 with a mass of 1. The item on the periodic table that has a charge of plus 1 with a mass of 1 is hydrogen. So when we're doing Bronsted-Lowry, we're going to be tracking the movement of an H plus from one substance to another. Definitionally, the important thing for you to know is the difference between the acid and the base. That the acid, as it says, gets rid of the proton, while the base accepts it. So with that said, look at this example here. You can kind of track it. We've got an acid here. All right, starts with H. We have we have a Arrhenius. Starts with H, clearly an acid. Water is interesting because it can be both. It can be either an acid or a base, depending on the situation. If water is interacting with an acid, then it will act as a base. Does anybody remember the vocab word for that? Let's write down the vocab. It's called amphoteric. An amphoteric substance can be acidic or basic. There it is. See it? An amphoteric can be acidic or basic, but water's pretty much the only one that we worry about it. But watch the proton move. Acids get rid of protons, an H plus. If you remove an H from HCl, he's just Cl. But there's also a plus. When you remove the plus, The neutral is now less positive, therefore it becomes negative. So the result after the Bronsted-Lowry of this acid is Cl minus, 1 less H, 1 less plus. But then there's the vocab. Whenever you change the substance, we automatically call it a conjugate, right? It's going to be the result of the change. It's a conjugate of the opposite type of species. So if it started as an acid, when you change it, it becomes a conjugate. Opposite species is a base. Look at the base, though. We know that Bronsted-Lowry bases accept the proton, the H+. So if you have water and you give it an extra H, it's no longer H2, it becomes H3O. But see how it was neutral? Well, we gave it a plus also. So it's H3O plus. It's a conjugate now because it's the change, and it's the opposite species. So it's an acid. Let's see if we can remember that we could do this last year. All right. Let's do some examples. We'll start with the acids. All right, so if something is acting as a Bronsted-Lowry acid, such as H2PO4 minus, all right, what we want to change that into, we're going to get rid of or add an H plus. Get rid of. Bronsted-Lowry acids, they donate away their proton. All right? So if we do that, we have to remove an H. So now it's not going to be H2, it's just going to be HPO4 because we got rid of a hydrogen. But now it's not going to be minus, it's going to be neutral because it was negative. I'm sorry, it's not going to be neutral. I trusted these kids sitting out here. It's going to be negative 2 because, teenagers. Because it was negative and we removed a positive, which makes it more negative, right? We removed an H and we removed a plus. Therefore, the negative became negative 2. And in regard to the vocab, we would call this a conjugate base. Conjugate because we changed it. Base because it's automatically the other type of species. Let's do another acid. CH3NH3 plus. Here's an important rule for Bronsted-Lowry. When we alter this dude, never pull from the middle. You see those H's that are trapped in the middle? That's a functional group. It's kind of organic chemistry beyond our scope. But whenever you're going to donate a hydrogen, donate it from the very beginning preferably, or the very end if you have to. Never pull from the middle. So, if we're going to, again, acid, if we're going to get rid of the H, this will become CH3NH2, because we got rid of one. We started as positive, so when we got rid of a positive, because it's an H+, the resulting charge is now neutral is the right answer. All right, yeah, we were positive, we got rid of the positive, now there's just no charge, and again, it's a conjugate base. All right, let's switch over to bases. Starting with Cl minus. All right, not an Arrhenius base. No OH there. But anyway, we know that Bronsted-Lowry bases accept the proton. So we want to give it an H+. If you give him an H, he becomes HCl. If you give him a plus, the charge becomes overall neutral. It was negative, but you gave it a positive, so it canceled out. So that is the entire Answer. And this is a conjugate acid. Conjugate because we changed it. Acid because it's the opposite type of species. All right, CH33N. CH33N. It's a base, so we want to give it a proton. Should I put it right there in the middle on that H3? No, don't go to the middle. You can go to the beginning or the end. If you put it at the beginning and it makes a substance you're not familiar with, then it's supposed to go at the end, but you're not going to lose points for that. But I'm going to put this hydrogen that it wants at the very end, and look how easy this is. It basically becomes CH33NH+. I added an H, I added a plus, and now I have my conjugate acid. Are we doing all right? You're very quiet. Well, this is the skill. Most commonly, we see it interacting in water. Tomorrow, when we start our advanced pH, there's going to be a whole lot of Bronsted-Lowry in water, so this next thing would probably be the most important. So let's check it out. The first one is HCl being added to water. So the trick here, if we're doing a Bronsted-Lowry, is to identify all the parts. All right, so HCl is clearly an acid. Starts with H, Arrhenius. Water is amphoteric, but since it's interacting with an acid, it will act basic. All right. We know that in Bronsted-Lowry, this is the direction of the hydrogen that moves, the hydrogen ion, from acid to base. And now we can predict those products. We're running out of time. So the acid minus an H plus will be Cl minus. The water with an extra H plus, what's the name of what's going to form there? Hydronium, yeah. One extra H, one extra plus. And it makes sense. If you dump acid in water, hydronium should flourish because it should be becoming acidic. This would be the conjugate base. This would be the conjugate acid. If you track the species that have changed, the acid turned into a base, the base into an acid. NH3, ammonia. Again, we are wondering what their Bronsted-Lowry interaction is in water. Hey, look at my different yield signs. They're correct the way that I wrote them. Why do you think I used a normal yield sign for the first sample? I bring clay because it's strong. Why do you think I used an equilibrium arrow for my second example? Because that's a weak base. That's what that next slide waiting for us that I'm going to have to do by myself because the bell's going to ring. But anyway, so here we go again. This is a weak base. You memorize that from Unit 2. Therefore, the amphoteric water will act as an acid. I know that we're going to have a proton transfer from acid to base, always. And I know that the result will be an acid. Well, let's do the base first. The base is going to accept that H, so instead of being NH3, he'll be NH4. But he'll be positive, because he also got a positive on top of that neutral. The water, if you remove an H, he becomes a little HO. But don't call him that. Instead, call him an O. But yeah, he's one less H, so it's HO or OH minus because he lost a positive. This will be a conjugate acid. This will be a conjugate base for all the same reasons that we've been going over. For video purposes, I'm going to keep teaching because I want the video to have what I didn't get to so you can watch it. But hey, let's keep going through the bell. The very last bit of slide is stuff you already wrote from Unit 2. Did you copy it again? I don't know. I kind of hope you did. But there's just one little weird thing that I didn't show you in Unit 2 that you need to see. It's dissociation equations. Bye. Have your slides ready for tomorrow. It's dissociation equations, but one of them is weird. So just to go through it, the very first one would dissociate at equilibrium because it's a carbon containing, it's aspen, because it's a carbon containing acid, so it's weak. And it would dissociate into H plus and C6H5A. We did that in Unit 2. The next one is barium hydroxide, which would dissociate with a normal yield sign, because that's a strong sample. Barium's one of those group 2 that makes it strong. And it would dissociate into barium ion and hydroxide. All right, just that dissociate, pulls apart. Exactly what we've been doing. Here's the weird thing, though. If you have a polyprotic acid, which is an acid with multiple hydrogens. Look here. Here's the last example. H2CO3. Carbon containing HO ratio, weak. If there is more than one hydrogen in your acid, it's going to break apart in what we call stepwise dissociation. Watch what happens. We're going to get out one hydrogen at a time. So the first dissociative step looks like this. Stepwise dissociation is when your acid has more than one hydrogen at the beginning. So when you start to dissociate it, you only pull off one hydrogen, leaving this. Look, there's still one on there because I only removed one. And then if the dissociation continues, which it will, you'll take that substance that you now have and dissociate it again, removing the second hydrogen. Again, one more time. Stepwise dissociation only happens when you are dissociating a polyprotic acid, meaning the acid you started with had more than one H. So you only got to remove one H at a time in concurrent steps. The room is totally empty. Look at it. It's just us. It's just us. Where all these people go? Where all these people go? What do y'all want to talk about? You want to do something different? You want to play tic-tac-toe? All right. You be X's. You ready?